Up next, we have Noe Dobrea. She'll be presenting, or he'll be presenting a paper on the rover science autonomy in the field, implementing the hypothesis map. Take it away.
All right. Thank you. Let's see. How do I start? There. Can you guys see all? Can you all see that?
Yes, looks great.
Okay. Oh, okay, great. So before I start, I want to give a nod to all the people in the team that have been working with me on producing this piece of work. This is an ongoing piece of work. It's part of a larger project known as TREX. This is not changing. There we go. Known as the Toolbox for Research and Exploration, or TREX, which is a survey node which aims to decrease risks to future missions by improving operational efficiency and science yield. It focuses on spectral characterizations of fine particles and the potential sources they may harbor. It also focuses on automated exploration of fine-grained surfaces. Here we discuss our plans for robotic exploration, for robotic field work, which in itself focuses on delegating mission planning data, collection, analysis, and decision-making to an automated robotic explorer. So I gave a talk about our project, the overview of our project at last year's Exploration Science Forum. I'm not going to go into the same overview because that would just be repeating things. I'm going to focus more into how this rover autonomy happens, what this so-called science hypothesis map is. So if you want to know more of the rest or what's around it, please look up this talk. It's online. So here's the premise. Basically, today's robotic exploration is centered around a very tight operator-robot command execution loop. Basically, you have a team of operators that carefully instruct the robot on navigation and target selection, right? And the robot executes the observation of the target selection, returns the data to the scientists who analyze it, and then they get together with engineers, they decide on what the next steps are, and you go on in this loop. It's very tight, it's very restrictive. Basically, you're just telling the robot to move here, to put the arm there, to acquire this small set of observations. In addition, so the process is a slow process. In addition, the data rates are pretty low, and the volume is typically limited. Even when we're going to be exploring something as close as the moon, we're still going to find that we're going to be data poor and volume poor. It's unavoidable because the amount of data that you want to acquire to make a good assessment of a site is always greater than what's probably going to be available. So the complete assessment of the field site is going to be rare. The activities are therefore are therefore decided upon based on limited knowledge of the site. So what comes out of this is that important observations may be missed, and historically they have been missed, where we have been able to realize something. So we came up with this new paradigm, which is basically a science autonomy. In this, basically, the rover activities are not uniquely prescribed by each iteration of commands sent from the operator, but instead they are open-ended and responsive to ongoing observations, even without iterative feedback from an operator. So basically, it starts with the scientist generating a set of hypotheses about the terrain they're going to analyze. For example, what's the geologic origin of this terrain? They basically insert this hypothesis, provide the hypothesis to the robot as a set of hypothesis maps, which we will discuss in a minute. The robot uses this information, as well as some explicit commands or constraints that the scientist may have wanted to provide as well, to determine a path of exploration and a measurement plan. It then autonomously executes this path, basically goes from site to site and performs the observations it decided it should perform. And based on the observations, it analyzes these observations, analyzes the data, and basically to address basically the hypothesis that it was tasked to test. As it basically performs the observations, analyzes the data, it updates the hypothesis maps and communicates that to the scientists. The scientists, with the updated concept hypothesis map, compare basically the results of the rover, and basically they reinsert a new set of hypotheses to the rover where necessary. For example, if the rover found something that was unexpected or did not fit within the parameters of the hypothesis map the scientists originally provided, then they use this new information to generate a new set of hypothesis maps, and you basically continue doing that. This explains the exact same thing, so I'm not going to go into that. So how does this work in reality? Well, in reality, we basically are going to go explore some sites. The sites that we chose for the first year include a volcanic flow near Flagstaff, Arizona. Here shown in 1, where it interacts with basically the underlying geology. And in number 2 is this basically purple spot in the Painted Desert. And I'm going to focus or exemplify on the purple spot because it's a really cool spot and I wanted to show it.
2 minutes.
But anyways, so the purple spot is actually is a erosional window into the Painted Desert. From far away, it already looks really interesting. The coloration is very unique. And as you get closer, why is it not getting closer? I guess you guys cannot see the video. Well, as you get closer, the amount of detail becomes astounding. You start seeing layering of all types of colors, including blacks and whites and reds and ochres, magentas, you name it. They're all seem to be there at a very, even at a level of a few meters per pixel. You can see that there's a lot of layering, a lot of details that basically an autonomous rover would be able to benefit from exploring. So the first step is basically to take the data, both visible, just imaging data, DTMs, terrain models, as well as hyperspectral images, basically spectral data, and basically start categorizing the terrain into different sets of terrains. For example, here the spectral parameter maps are generated where you look at absorptions and different absorptions of the spectra and parameterize them so you can see their distribution spatially. So each of these maps is basically the spatial equivalent of the original map, but with the different spectral parameters. You can also take it a step further and actually infer mineralogy. So basically here, the reds represent the distribution of these different minerals in the different locations of the map. So once you have the minerals, of course, so you will went from spectral features to mineralogical constraints based on the spectral features. And once you have mineralogical constraints, well, then you can infer geologic origins. Now, as every geologist here knows, is that any one mineral or most minerals can have more than one possible geologic origin. So there's an ambiguity there. And that is basically the error in your interpretation, right? It's basically, okay, so I see mineral X. Well, the mineral X could have been formed by pedogenic, or it could have been formed by igneous processes. So which one is it? Well, that's the ambiguity that the rover is, or an astronaut or a person would like to be able to disambiguate. So that's the task of the rover. So this is where the hypothesis map comes in. Basically, imagine the same maps I presented before. Every plane is the exact same terrain that we had before, but every plane represents a different geologic origin. So X, Y is the spatial dimension, Z is the geologic origin, and the value of the pixel is the relative likelihood of the geologic origin for that pixel location. So for a pixel that has high values, it's on, for example, the igneous plane, it's more likely that it has an igneous origin. As you can expect, different planes will have higher values greater than 0 on the exact same pixel because of the ambiguity, and that basically is the uncertainty in the process. So the more uncertain it is, the more likely the rover is going to want to go explore that place to disambiguate. And on the other hand, the more minerals that you detect on a specific pixel that support the geologic origin, the higher the probability value for that pixel. And yes, we can infer the presence of more than one mineral from a spectrum. So the rover's job is basically to disambiguate the geologic origin for its terrain. Here's an example of the geologic origin cube that I just showed schematically before. And basically, we see different types of geologic origins. And as I said before, the uncertainty for each pixel increases with the number of planes with non-zero value for the pixel. So in some cases, it's very ambiguous. Basically, a lot of planes have this non-zero value. But in other cases, for example, for evaporitic, it's not as ambiguous. And in some cases where the value is greater, that is particularly high, there's a higher likelihood that this is a correct interpretation. So basically, the rover's task is an optimization problem.
We're going to have to wrap it up. Yeah. We're at your full 12 minutes.
Oh, sorry about that. My bad. Okay. Anyways, the rover plans a trajectory, optimizes the trajectory, checks waypoints. The scientists can also input the waypoints, uses the spectrometers to analyze the terrain. And basically, from a specific spot, uses basically the geologic origin table to update the hypothesis map and send that back to the scientists. And that's basically the general idea of this. I'm going to leave you guys with this slide here. The idea being that overall you get an increased science yield because data analysis is not dependent on the data volume limitations. And my apologies for overextending my talk.
All right. Okay, thank you. Hopefully there'll be some good questions in the discussion session for you, Eldar.